Why is gravity so weak compared to other forces? Could higher dimensions be the answer? Physicists believe that higher dimensions might exist, not just as an intellectual exercise. One important reason is that the existence of these higher dimensions could help uncover some of the universe's mysteries. For example, the existence of higher dimensions could explain why gravity is so weak. Among the four fundamental forces, as we discussed earlier, gravity's strength is extremely weak and cannot be compared to the other three forces. The weak and strong forces, along with electromagnetism, also have varying strengths, but gravity is much weaker compared to them. Physicists truly do not want to see this inconsistency, and although they often argue about many things, they usually long for harmony and unity in physical laws. One of the many questions about gravity is, what does it mean that gravity is so weak? Why is gravity so much weaker than the other forces? More dimensions could potentially explain this phenomenon. Most forces become weaker as the distance increases, and the rate at which they weaken depends on the number of spatial dimensions. The more dimensions there are, the more the force is diluted into those additional dimensions. Imagine someone opens a stinky tofu at a party. What happens? Of course, the closer you are to the tofu, the stronger the smell, and the further you are, the molecules of the stinky air will spread into the air and get diluted. Now, let's change the situation. If the person opening the stinky tofu is in a narrow corridor, then everyone in the corridor will smell a strong odor. If the person is at an intersection of several corridors, the smell will spread in different directions, and people in the other corridors will smell less of it. The rate of dilution of the odor depends on the speed at which fresh air is supplied. The more corridors there are, the more fresh air there is, and the faster the dilution. Even though there is no smell, forces also have this characteristic. If there are two additional spatial dimensions beyond the three we are familiar with, the force exerted by an object on us, whether it's gravity or electromagnetism, will not only spread in the three dimensions we occupy but also spread into these additional two dimensions. Therefore, when we move away from the source of the force, compared to a situation with only three dimensions, the force will weaken faster. It's important to note that these extra dimensions must be smaller than 1 centimeter in size, as we have not discovered them yet. Only gravity is influenced by these dimensions, meaning that other forces cannot spread into them. If there are fourth and fifth dimensions, they must be smaller than 1 centimeter and must be ring-like, and only gravity can spread into these two dimensions, while other forces cannot. So what would happen? The gravitational force between objects less than 1 centimeter apart would be diluted into the other two dimensions, and the strength of the force would decrease very quickly as the distance increases. For distances greater than 1 centimeter, these two dimensions would no longer play a role in diluting the force. This could explain why gravity is so weak. For objects very close to each other, gravity's strength is the same as the other forces, but once the distance exceeds 1 centimeter, most of the gravity is diluted into the other dimensions, leaving the remaining force very weak. Of course, this is still just a hypothesis, so don't take it too literally. The 1 centimeter is just a way to illustrate the point, not a rigorous scientific definition. Does gravity really behave like the smell of stinky tofu in the corridor, getting diluted? Even if we are not sure about the possibility of more dimensions and their effect on weakening gravity, it is still at the theoretical level. Surprisingly, we have other ways to look for additional dimensions. The idea of more dimensions sounds good, as it could simply and intuitively explain why gravity is much weaker than the other forces. But you may have realized, this hypothesis is actually easy to test. All you need to do is measure the gravitational force over a very short distance. If the gravitational force is strong at very short distances, it would indicate that small ring-like dimensions exist, because at such a small scale, the gravitational force has not yet been diluted. Unfortunately, it is not easy to do this. Measuring gravity sounds like a simple task. For example, when you weigh yourself, you are measuring the gravitational force. But that's because we are used to measuring it over long distances. When you stand on a scale, you are measuring the gravitational force between you and the entire Earth. Don't forget, both of you have quite large volumes, and your distance is the radius of the Earth. Measuring gravitational force over short distances is a completely different matter. If you want to measure the gravitational force between two objects 1 centimeter apart, you must ensure that their distance is no more than 1 centimeter, which means that they must be very small. This also means that they will not have much mass, and if the mass is too small, the gravitational force will be too weak to measure. For example, the gravitational force between two bearing balls 1 centimeter apart is smaller than the weight of a grain of dust on Earth. However, physicists have a characteristic: impossible things excite them even more. More importantly, this experiment could potentially confirm the existence of extra-dimensional space. There will always be particularly smart people coming up with creative ideas to design various experimental plans. These experiments are very complex, so we will only discuss the conclusion. In the past few years, physicists, through tireless effort, have measured how gravity changes with distance on a millimeter scale. They found that at least at distances of 1 millimeter, gravity's strength still follows the same pattern as on a larger scale. However, this does not mean that extra dimensions definitely do not exist. This result only suggests that if these dimensions exist, their size must be smaller than 1 millimeter. Physicists have another characteristic. For phenomena that have not been confirmed or denied through actual measurement, theoretical physicists will freely come up with ideas. After all, it hasn't been confirmed yet, so why not think about it? Physicists can say that this theory applies at scales lower than what current experiments can measure. So, in this matter, the only thing we can be certain of is that if other dimensions exist, they must be smaller than 1 millimeter. How small they are, no one can say for sure. Measuring gravity can help detect whether other dimensions exist, but it is not the only method. Particle colliders can also help people detect other dimensions. These machines, which cost billions of dollars and stretch over 20 kilometers, can not only discover the Higgs boson but also potentially discover other things. So how can we use particle colliders to explore other dimensions? Imagine that you have a tiny particle in the palm of your hand, say, an electron. This particle might not only exist in the familiar three-dimensional space but could also be moving in other dimensions. These dimensions are ring-shaped, so in the dimensions we are familiar with, this example appears stationary. But what would the motion of this particle in the other dimensions affect? If this particle also moves in the other dimensions, it means it has momentum in those dimensions, which means it has additional energy. Since this particle does not move in the dimensions we are familiar with, the additional energy will manifest as additional mass in our perspective. This is based on Einstein's theory, where mass and energy are closely related. In other words, if the particle moves in the other dimensions, you would find that it is heavier than the particles that do not move in those other dimensions. This is the method we use in particle colliders to explore other dimensions. We collide particles, and if we find a particle that looks very much like an electron, with the same electrical charge, spin, and other properties, but it is heavier than a normal electron, we have reason to suspect it might be an electron moving in other dimensions. In fact, if other dimensions do exist, we should be able to find partner versions of known particles, with the only difference being that they have greater mass. Many spatial theories predict a specific particle structure called the Klein bottle. We often talk about the Klein bottle representing four-dimensional space. It is the same name. These examples can be arranged at fixed intervals according to their mass. If we can find such a group of examples that can be sorted in a regular manner, we can prove the existence of extra-dimensional space. In this tower, from lightest to heaviest examples, the lighter the mass, the fewer the dimensions in which they move. Examples that move in 5-dimensional space are heavier than those moving in 4-dimensional space. Let's continue the discussion. What else does the existence of more dimensions imply? Even if these extra dimensions are extremely small, if they exist, there are other interesting consequences. According to physicists, the reason gravity is so weak is that its strength is diluted by the other dimensions. In other words, gravity is originally just as strong as the other forces. It is not a weakling, rather, it is a superhero disguised as weak. This means that creating black holes is not as difficult as we once thought. Typically, you would need to compress a large amount of mass and energy into a very small space to create a black hole. However, particles, especially those with similar charges, like protons, don't like to get too close to each other. We would need some catastrophic event, such as a cosmic collapse, to push enough particles close enough together to reach the critical density required to form a black hole. But if the gravitational short-range force is strong, then an enhanced version of gravity could make the process of proton formation into a black hole much easier. Even a Large Hadron Collider could achieve this. If there are dimensions smaller than 1 millimeter, a large particle collider could create a black hole every second. Doesn't that sound a little scary? Wouldn't these black holes grow larger and eventually swallow the Earth? The answer, of course, is no, because, as we can clearly see, the Large Hadron Collider has been running for so long, and our world is still here. The good news is that, even if the Large Hadron Collider could create such small black holes, their power is far less than that of the large black holes formed by stellar collapse. These little guys evaporate so quickly that they won't even have time to swallow the Earth. According to Hawking's theory, the smaller the black hole, the faster it evaporates. A black hole with a diameter smaller than 1 millimeter would evaporate so quickly that it would be gone before we even noticed it. Another reason to relieve your worries is that high-energy particles have been bombarding and colliding with the Earth for billions of years. If particle collisions could truly generate black holes large enough to swallow planets, this would have already happened long ago, and we wouldn't even exist. Now, speaking of dimensions, we have to mention a theory called the string theory. We briefly mentioned it earlier, and now let's dive deeper into it. Physicists have long tried to describe all the fundamental forces, gravity, strong force, weak force, and electromagnetic force, with a unified, self-consistent, and complete theoretical model. Whether or not this theory exists, it is an extremely noble goal. Though the final answer is still far away, humanity has made significant progress. In this process, physicists have proposed some interesting candidate theories, one of the most important of which is string theory. String theory suggests that the universe is not made up of zero-dimensional point particles, but is composed of tiny one-dimensional strings. How small are these strings? They are on the scale of 10 to the power of -35 meters. We won't make analogies, but for the average person, it's impossible to imagine such a small size. In theory, these strings can vibrate in many different ways, with each vibration mode corresponding to a different particle. When viewed from a distance, these string-like structures are not noticeable. People tend to think of them as point-like particles. This theory has one feature: if more dimensions are introduced in this theory, the mathematical description becomes simpler and more natural. String theory also has branches, and each branch predicts a different number of dimensions for the universe. Superstring theory suggests that the universe has 10 dimensions, while bosonic string theory predicts 26 dimensions. Regardless of how many dimensions there are, where are these extra 20 or more dimensions? Why haven't we discovered them? Similar to how string theory tries to explain why gravity is so weak, the extra dimensions in string theory are also self-contained, closed, ring-like dimensions, rather than infinitely extending straight-line dimensions. Finally, let me summarize. Understanding the geometric structure of the universe is a very basic step in understanding the world. In the process of uncovering the truth of the universe, you will find that the world is not what we imagined. This process will give you an unparalleled sense of satisfaction. Of course, in addition to providing satisfaction, searching for other dimensions also has some practical significance. Perhaps we will discover that these dimensions have other uses, such as storing energy or allowing us to access spaces previously unreachable. Who knows, they might even have other amazing functions. Furthermore, finding other dimensions can help us study how the universe operates, which is the 95% of the universe that we still don't understand. Even if we eventually discover that these dimensions don't exist, this conclusion is still important. With this conclusion, we can begin to explore why space only has 3 dimensions instead of 4, 37, or even 1 million dimensions. What's so special about 3-dimensional space? So far, experiments measuring gravity at short distances have not yielded any unexpected results. The Large Hadron Collider has also not discovered any black holes or particles moving in other dimensions. In other words, there is still no evidence to suggest that the string theory's description of the world is correct or that gravity can spread to other dimensions. We still don't know how many dimensions the universe actually has. What's even stranger is that there is a possibility that different regions of the universe may have different dimensions. Perhaps only our small section of space is 3-dimensional, but other parts of the universe may have 4-dimensional or higher-dimensional spaces. If you've read the three-body problem, you are probably familiar with this concept. So, that's all for this episode on dimensions. See you next time on Cosmos Unlocked.